Another example on the amplifier circuits of the bipolar junction transistor, we have this amplifier circuit. Here the voltage source is VCC, then RC, and as you see the base is connected to the ground, the signal or the input is connected here, the output is taken from here. So the first question that we usually ask is, what kind of amplifiers is this? Which amplifier family does this amplifier belong to? So we look at the input. In order to answer this question, we look at the input. The input is connected towards the emitter. The output is taken from the collector. So this is a common base amplifier. So this is called common base amplifier. Okay? So we need, it's given that IC is 1 milliampere, so the DC is solved. But remember that usually we have to solve the DC first. You have to plot the DC circuit first, solve it to get the IC, to get all the currents, the DC currents, and then you calculate the parameters. Not here, for simplicity, I'm giving you the DC value of IC, beta is 100, early voltage is infinity, which means that you ignore RO. RO will be infinity, okay? So you don't use RO. So let's go directly to the AC analysis. Of course, you have to calculate the parameters. You have to calculate R pi, RE, GM, and RO, of course, here is infinity because early voltage is given as infinity. You have to calculate RE, R pi, GM, and then we go to the AC analysis. When we do the AC analysis, let's always start from the input signal, V signal. So we have, this is our V signal. We have a resistance R signal, and you go step by step. The capacitor is short circuit, and then we reach to the emitter of the transistor. And then we have, this is a DC current source. DC current source will be open circuit. So this DC current source will be removed, it's open circuit. And then we go to the emitter. So we go to the emitter of the transistor. So the transistor will look like this: base, emitter, base, collector. The base is connected towards the ground, and the collector is connected to a resistance RC towards this DC source will be deactivated, which means it will be connected to ground. So RC to ground. So the collector is connected by RC to ground. And then the collector is also connected by a capacitor, which will be short circuit, and then RL to the ground. Capacitor short circuit, and then RL to the ground. And we are taking the output from here. This is the output. And then now it's time to replace our transistor with a model. Which model do you think it fits here, or it will make this circuit easy to analyze? If you use the pi model, you will have a resistance between in the base and dependent source, and then both of them will be connected to the emitter. This is not efficient here. You can use it and you will get a solution, but it's not efficient here. It will be difficult to analyze, maybe a little bit difficult. Okay, so it's basically here it's easier to use the model where the base is ground or the base has nothing, right? Like the T model. So if we use the T model, we have a resistance called RE, and we have a dependent source here, which is alpha IE, or you can also use GM-VBE, and then the base is here connected to the ground. Why this model is easier? Because now, since you have a ground in the middle, you can separate the circuit into two parts. You can separate the circuit into two parts. So you can do the following. You can, of course, where is IE before we separate? This is IE. This is the current IE, and this dependent source is alpha IE. Now you can separate the circuit into two parts, right? So you can do the following. You can say that this dependent source goes to the ground, and this resistance goes to the ground. And the ground here is the base. This will make your circuit easy to analyze, right? Now you can plot your circuit in a different way. Maybe we can get the resistance, this resistance here, just to be familiar. But remember, if you get this resistance vertical, IE is going from the ground, which is from the base up, right? So you can plot this like this. You can put a resistance RE here like this, and IE is the current going from the ground up. Now the circuit is kind of familiar, easy to analyze. We need to calculate our input looking from this point after our signal, directly after our signal, so we need to calculate our input from here. And of course, if you calculate our input from here, you forget everything before, so you will see only what? You will see only RE. So our input will be RE, which is VT over IE, which is VT over IC over alpha. So 25 millivolt over IC over 1 millivolt, 25 ohm multiplied by alpha, it will be around 24.75 ohm. This is our input. And then we need to calculate V output over V input, where V input, by the way, is defined to be the voltage of this point. V signal is the voltage of the source. V input is the voltage after our signal. So we need to calculate, so V input is the voltage here. We need to calculate V output over V input. Of course, both of them, we can calculate them in terms of IE, because the current here is alpha IE. So forget about now G and VBE. The current of the dependent source is alpha IE. So we can say that V output over V input equals. V output equals what? V output, the voltage here, it's the same as the voltage here, equals the total current multiplied by the total resistance. Total current, alpha IE, it will go through the total resistance, RC parallel with RL. So alpha IE multiplied by the total resistance, which is RC parallel to RL, right? We have a total current here, alpha IE. This total current will go through these two resistors together, RC parallel with RL. But since it is going from the ground up, the current direction is this direction, from the ground up, V output will be negative. Now, let's look at V input. V input also can be written in terms of IE. We can say that V input equals IE RE. But IE is going up, so it will be negative IE RE. Now, the current IE will cancel with the current IE, and this is important. Don't get an expression in terms of I or V. The expressions, all the expressions must be in terms of constants, of your constants, the resistors, alpha, beta, okay? Don't get an expression in terms of I or V, because we don't know I and V. These are variables, right? So we have to get the expression so that the variables, they cancel with each other. So what we'll get here, we'll get alpha, RC parallel with RL divided by RE. And then we need V output over V signal. V output over V signal, we already calculated V output over V input. And as you see, this is repeating with us. We already calculated V output over V input. So we can say that V output over V signal equals V output over V input multiplied by V input over V signal. This is a common procedure that we usually use to even simplify the calculation of the gain. Even if I don't ask you to calculate V output over V input, try to divide the gain into stages. V output over V input multiplied by V input over V signal. Even if I don't ask for it, for V output over V input. We already calculated V output over V input. So remaining is V input over V signal. What is the relation between V input and V signal? V input over V signal, the relation between them is the voltage divider rule. It will be RE over the sum, right? So we can say here that V output over V input is alpha RC parallel with RL divided over RE multiplied by V input over V signal, which is RE divided over R signal plus RE. Of course, RE will cancel with RE, and you will get alpha RC parallel with RL divided over R signal plus RE. The gain here, the gain between V output and V signal, it will be in the range of 0.6. So the voltage gain is less than 1, which means that the output voltage is less than the input voltage. In case that you have a load, so the output voltage will be less than the, even if you don't have a load, the output voltage will be less than the input voltage. Okay, but the gain from V output to V input you will find it to be high. So V output over V input, you'll find it to be in the range of 123. So V output over V input will be in the range of 123. But when we continued the gain from V input to V signal, it was very small. We multiply by V input over V signal. Usually RE is very small. RE is usually very small. And if our signal is high, like in our case here, our signal is 5 kilo ohm, it's in the same range of the load, same range of RC, okay? This will reduce the gain very much. It will take big part of the input voltage. And as we said, if the source voltage is high and the input resistance is low, the input resistance here is low of this amplifier, very small, 24 ohm compared to the resistance of the source, then the resistance of the source will take most of the gain. It will take most of the input voltage, right? And this is a big disadvantage here. The big disadvantage for this amplifier circuit is that the gain will be reduced very much because of our signal. If our signal has like a value that is comparable to RL, RC, a value that is higher than RE, okay, then the gain will be reduced very much. It will be reduced from 123 to 0.6, as you see. Which means that you don't get any voltage gain. Actually, the voltage is going to be decreased. Okay? So now we calculated V output over V signal, V output over V input. We can also calculate the current gain. I load, the ratio between I load, the current that will go to the load, and I signal, the current of the source. The current that will be going to the load, you can write an expression for it by a current divider. It's the total current here, it will be divided by these two resistors. So it will be, the total current here is negative alpha IE, negative alpha IE, multiplied by this resistance over the sum, the other resistance. So in the current divider rule, you multiply by the other resistor. So you multiply by RC over the sum. What about I signal? I signal, the current of the source is negative IE. It's negative IE because IE is going up here. It's the same value as I signal but opposite direction. So I signal is negative IE. When you divide now IL over I signal, what you will get alpha RC over RC plus RL. So even the current gain will be less than 1. So no voltage gain, no current gain. So the current gain will be small here. The current gain will be in the range of 0.609. This is the current gain. Last part is we need to calculate our output at this point, directly before RL. So before RL, we need to calculate our output. So what we are going to do is, we are going to forget about everything before the point, our output from here, and deactivate any independent source. So we are going to deactivate this source, so it will be 0. When we deactivate this source, the current here will be 0, IE will be 0, and this dependent source will be also 0. Current source with a value 0 means open circuit, so the only resistance that you will see, our output will be only RC, which is 8 kilo ohm. Again, when you deactivated the source here, the current in this loop became 0. When the current here, IE, became 0, the dependent source became 0, which means open circuit because it's a current source. And then the only resistance that you will see when you look from this point is RC. Okay, so that's it for this example. We'll see you with another example in the next video.